Good morning, class. Today in climatology, we'll be looking at the heat flow theory. So, what exactly we will be seeing in this is trying to understand how exactly the heat flow happens. So, the transfer of heat is basically how it is categorized and how it is like in like with respect to your building. How does it happen? Okay. So, starting with this, will be the topics that will be discussed will be the basic principles of heat transfer, the performance of different materials considering the value, the time lapse, and the decrement of the building element. So, looking at the basic principles of a heat transfer, we'll be looking at how exactly is transfer. So, heat can travel from one phase to another in three phases. That will be your convection, convection, and radiation. Now, your both convection and convection require matter to transfer heat, whereas during the radiation, it is like through the transfer of heat is happening will be through the around surrounding medium. Yeah. So if there is a temperature difference between two systems, heat will transfer will from one phase to other, and will always find a way to transfer from a higher to a lower system as a result of second law. So the transfer of heat is basically dependent on the second law of thermodynamics, which is nothing but the transfer happens from a higher system to a lower system. So there's always a cycle that's going. So when there is a temperature difference between objects in proximity, the heat transfer between them can never be stopped. It can only be slowed down. The greater the temperature difference, the faster is the rate of heat flow. So this process can never be stopped. There's only it will be like very even if there's minimum, it can only be slowed down to in very minute character. It can only be slowed down. It can never be stopped. So this transfer keeps on happening, and because this is dependent on as we spoke about the second law of thermodynamics, it's going to be transferred from a higher system to a lower system, and can never be slowed down. So looking at your heat transfer, so heat transfer is nothing but the transition of your thermal energy from a heated item to a cooler item. So when an object or a fluid is at a different temperature than its surrounding or another object, the transfer of the thermal energy, also known as the heat transfer or the heat exchange, happens. So it's talking about how this transition happens. So it's talking about a difference in temperature as we spoke about from the higher medium to a lower medium. So the heated element to a cooler element, the transfer of heat happens. So this heat transfer, why does it actually occur? Why do we, I mean, why is this necessary? So this heat transfer occurs in a way that the body and the surrounding reach the thermal equilibrium. So it's talking about coming to a state where there is an equilibrium of all the like temperature. So coming at this point, we're looking at how the heat transfer is usually associated with the carriage of heat or phase change by a substance. So even this heat transfer is usually associated. How when exactly is this like too obvious is when there is also heat transfer is happening during a phase change. We know what exactly a phase change. Usually, like you know how when we heating a liquid, it turns into a vapor, right? It's talking about the solvents from the steam to the from water to steam to the vapor, and the transfer is happening. It's letting out heat. So this transfer is nothing but it during the stage of boiling this happens. So it can actually be fundamentally treated as a variation of a convection heat transfer. So even that is a form of heat transfer. So in each case, what it is the basic driving force is nothing but the heat transfer is a difference in temperature. Going back to your second law of thermodynamics, so it's talking about a basic temperature difference is enough for the heat change, heat transfer to happen. So let's looking at this diagram, let's try and understand what's trying to happen over here. Is like can you see like how when where the heat directly reaches the pan ends up becoming heats up. So it is like a conductor. So the heat transfer is happening through conduction. Yeah. Whereas the medium, the water that is inside, due to the heat of the pan, it ends up boiling, and it tries to attain if the transfer of heat happens. And that transfer that is happening is because of that's called convection. And what is the air or the medium that is like nearby to the fire ends up heating up and promotes the radiation. Okay, why exactly do we have to see all of this? Is because let's try looking at how this transfer of heat goes about in a building. So in a building, can you see the floor that is there? You could see about how this heat transfer is happening. Yeah, he's talking about convection. It's directly like on the earth, and how the heat or the energy, like whatever it is, would feel. So you understand like why people actually prefer. I mean, the chlorine is actually dependent upon the climatic conditions of a place. Because see, like in Kashmir, you know, they try and use wooden flooring because they talk about how it's a good, bad conductor of heat, or I mean, like heat and convection. So that's why the cold, this thing, it doesn't transfer to the flooring. So that's why it's preferred. So whereas in the other condition, we talk about how this heat is transferred, or even how you could use it to your advantage. As humans, and also the materials we were talking about previous chapters and topics, we were talking about how this thing goes about how you as a being member also radiate energy or heat. Yeah, and you could also talk about how your building itself as a whole conducts the heat that is outside. Yeah, so it also becomes a part of a conductor. So it's or even the conduction happens in the spaces your building, your walls would also feel warm or cold. Yeah, and then also about how the because of this the air around it, the medium that's here, the air around it ends up becoming the transfer of heat or energy that happens in the convection factor, and how the roof ends up being the radiators and so on for the radiation. Yeah. So to try and understand how this heat transfer happens, we are going to look into these basic factors. So that would be your convection, convection, radiation, and phase shift. So what exactly is convection? Convection is nothing but the transfer of heat by the electron diffusion or the photon vibration. That is basic concept of a heat, how it's generated and how it's conducted. Yeah. Whereas in convection, it is a transfer of heat by conduction in a moving medium. So it requires, in a convection, it requires a medium for it to move it, because such as a fluid. Whereas radiation, it requires it's basically by electromagnetic radiation or equivalently by photons. Yeah? Then what exactly is phase change? Phase change is nothing but the transfer of heat with the potential energy associated with the heat of phase change, whether such as boiling, condensation, or freezing. So it's talking about how during these factors there is heat transport. These are like key elements that we would be looking into. Yeah. Then heat. What exactly is heat? Heat is nothing but your transfer of thermal energy from a hotter material to a cooler material. This heat transfer may change the internal energy of materials. So it's talking about how the overall heat transfer and how does it affect and what exactly is heat. What do you mean by internal energy when you're talking about internal energy? This internal energy is nothing but we are talking about how this heat is generated, the kinetic energy and thermal energy, right? So during seeing those factors, we're talking about how the internal vibrational energy that the molecules or electrons composing all the materials contain, that is except at absolute zero. So conduction. So now we'll be going into deeper topics. We'll be trying to understand all these factors and how later on we'll be trying to understand how these factors affect us. Yeah. So in conduction, so conduction is nothing but the transfer of thermal energy from a region of higher temperature to a region of lower temperature through direct molecular communication within a medium or between mediums in a direct physical contact without a flow of the material medium. It's talking about how the transfer basic conduction concept is like requires a direct physical contact is involved, and it's a basic transfer of heat from a higher temperature to a lower temperature. Yeah. So where it has to have some kind of a communication. Okay. So in other words, what it's trying to say is heat is transferred by conduction when the adjacent atoms vibrate against one another or as electrons move from atom to atom. So how this conduction, the heat, this heat transfer is happening, is talking about is the adjacent atoms, they actually vibrate. They have to be in very close contact. So as they vibrate, they against one another, the electrons move and the heat is actually getting transferred from one place to other. Yeah. So this conduction, as we have already learned, is that conduction is greater in solids where atoms are in close contact, and in liquids or gaseous metal, because the molecules are usually apart, there is a lower chance of molecules colliding and thereby passing the energy. So that's why your conduction is reduced. Yeah. So what it's trying to say is that the lower the conductivity, the better insulator a material. So thereby you can subcategorize this conduction. If the conductivity is better, it has good conductor, or if it's like a bad conductor, it will end up being an insulator. So talking about an insulator, insulator are usually have high resistivity. So resistivity is nothing but the reciprocal of this resistivity is the reversal of your conduction. So this is basically how this is denoted by 1 by K, measured in units of meter degree. The better insulators usually have high resistivity values. That's what we are talking about. So density is often an indicator of conductivity. So higher density materials have higher K value, but it may not always be true. So talking about how, though our liquid materials are denser, they don't have as much of a conductivity. So they are like, you could not like, define that denser materials are good conductors. There are a few like exceptions that we do in such cases. So the relationship is due to the fact that the air has a low conductivity value and that lightweight materials tend to be porous, thus containing more air, their conductivity tends to be less. It's talking about how, due to the porosity or the value, the air is contained in those elements, and thereby, because air is a very low conductivity, it thereby ends up reducing the conductivity of the whole material itself. So it's talking about how, irrespective of the density or irrespective of the like the character it is, if it is a porous element, the air, due to the air, like the conductivity tends to be less. So looking at this, so what you're talking about, the molecules in two bodies are at different temperatures and have different kinetic energies. So the collisions occurring at the contact surface tends to transfer the energy from high to low regions of the low temperature. So the trapped, if it was a single element, yeah, a single glass panel or a single wall, what happens is that you have one side with a higher temperature and the other side with a lower temperature. So even though a single side of the wall has a higher temperature, these molecules end up like colliding with one another and transferring the energy and the heat to the other elements on the lower side. So what happens is that the transfer of heat happens from the one phase to the other. Whereas we could look about the other, like how do you avoid this? We could always try and add air, or the how we are talking about porous elements. Instead of adding the porous elements, we can actually add an air gap. So basically, what happens is that the trapped air between two layers of glass ends up becoming a very good insulator and thereby reduces the convection heat. So how do you actually then try to avoid this? Is what they've tried to give an example of how they've actually tried to input the idea of adding air into the element, keeping a gap so the heat transfer doesn't happen by convection. Okay. So talking about the heat loss rate, we can see the heat transfer by convection can be used to model heat loss through a wall. For a barrier of constant thickness, the rate of heat loss is given by this formula. So it's talking about how, it's talking about the heat, you can see the T temperature hot and the temperature cold. So it's a two difference in temperature. So this heat loss rate is given by Q by T. But Q is nothing but your area into your inside temperature minus your outside temperature divided by the thermal resistance of a wall. So using this, you could try and derive like what exactly is the heat loss rate. So it's actually usually a very important factor when you try and understand how you could your building as a barrier, how it is affecting, and how it could actually be used for your advantage. So that is looking at your convection or looking at your convection. So convection, the transfer of heat by bodily movement of carrying medium. Okay, so it may be due to a forward force alone or such generating, or maybe propelled by an upright force. So during when all of this factors go about, how does this happen? I mean, the transfer of heat happens. So what we say is that the rate of transfer in convection differs from three factors. That is your temperature difference, the rate of movement of the carrying medium in terms of kg per second, meter cube per second, the specific heat of a carrying medium given by joules per kilogram degree Celsius or joules per meter degree Celsius. So these qualities were used in ventilation figures or cooling calculation. So talking about how all of these things are actually very important and how these actually end up becoming very important elements in calculating your ventilation figures or your cooling calculations. Yeah? So convection is a heat transfer by mass motion of a fluid, such as air or water, when the heated fluid is caused to move away from the source of heat, carrying energy with it. This movement occurs into a fluid or within a fluid and cannot happen in solids. So in solids, molecules keep their relative positions to such an extent that bulk movement or flow is prohibited. So what exactly is happening is like the movement is dependent upon a fluid or something, right? So whereas what happens is that in solids, the molecules keep the relative positions to such an extent that the bulk movement of the flow is prohibited, and thereby convection does not happen. In natural convection or the fluid surrounding the sensors, it receives the heat and thereby becomes less dense and thereby rises. So how this flow is actually happening is what we will see. So how it happens is that the surrounding, the cooler fluid, thereby then moves to replace it. This cooler fluid is then heated and the process continues. So we have actually already seen a few topics about how this later further dates we'll be talking about how this courtyard effect and a stack effect goes about is basically on this concept of your convective driven pattern. So in this, the driving force for natural convection is your buoyancy. A result of differences in the fluid density when the gravity or any type of acceleration is present in the system. So forced convection by contrast occurs when the pumps, fans or other means are used to propel the fluid and create an artificially induced convection current. So this forced heat convection is sometimes referred to as heat advection or sometimes simply advection for short. So what exactly is it? So it's talking about how your natural driving instead of the natural driving factor, the heat is getting transferred because of the heat. So you talked about how the hot air becomes lighter and it moves up and the colder air is denser. So thereby, as it moves up, there is a cycle that keeps on happening. Or sometimes even this in few scenarios you talk about your forced convection. So where the convection it talks about with the pumps, fans, or these things are used to propel the as you switch on your fans, you can see that immediately the hot air is usually on the top of the room. So, but immediately, a moment all the hot and heated air rushes down. So it tries to that cycle is like created as the cycle continues on. It tries to cool down. That is how a basic concept works. So that was your convection. Then talking about the radiation. So radiation is nothing but the transfer of heat energy by the electromagnetic infrared rays, and it's very different compared to your conduction and your convection. So your convection and convection, what happens is it takes place when the material being heated is in direct contact. So these two require direct contact, whereas it is talking about you don't require actually a medium, but the nearby air itself like acts as a medium. So infrared heating, there is no direct contact with the heat source. The infrared energy travels in straight line through space or even vacuum. Okay, so similar to light and does not produce heat energy until absorbed. So this rate of emittance and absorption of heat by radiation is usually affected by so many factors. That will be a surface temperature, the color and the texture of the surface, and your surface area. Okay, so we have looked about the basic concept of these readings. Now, looking at the different other, now as we are going about, let's try and advance ourselves. Let's try and understand few more concepts that we will be looking at. So, looking at this, what exactly is a specific heat? So, specific heat is talking about all materials contain or absorb heat energy in different amounts. The quantity of heat energy or thermal capacity of a particular material is called a specific heat. Yeah. So the quantity, how much it would the thermal capacity of a particular material is called a specific heat. The specific heat of a substance is defined as the amount of heat energy required to cause a unit temperature increase of a unit mass of a substance. The unit of measurement is usually given by joules per kilogram degree Celsius. The higher the specific heat of a substance, the more heat it will absorb for a given temperature range. And then looking at what exactly is your latent heat. Your latent heat is nothing but the amount of heat energy that is absorbed by unit mass of a substance at the change of state. That usually that happens during the phase change is what we are turning from solid to liquid or liquid to gas. So if you see an example about how it is, for the latent heat for water or of fusion, what happens would be 0 degrees Celsius ice to 0 degrees Celsius water. It would be 335 kilojoules per kilogram of evaporation at 100 degrees Celsius. So at 100 degrees Celsius, what happens is 2,261 kilojoules per kilogram. So of evaporation at 20 degrees, it will be 2,400 kilojoules per kilogram. So talking about the thermal capacity, specific heat we spoke about when the thermal capacity. So thermal capacity is nothing but the product of a mass, okay, the overall mass and the specific heat of a material. So talking about the two things put together is what will give you a thermal capacity. It is measured as the amount of heat required to cause a unit temperature increase of the body. So unit is given by joules per degree centigrade. So you spoke about conductivity, conducting all of those matters, right? Now let's looking into more detail of this. We will be looking at what now the conductivity. The conductivity, the rate of heat flow through varies with different materials and is described as the property of the material. Is thermal conductivity is usually given by the value K value. Yeah. So thereby resistivity would be 1 by K. Okay. So let you, it's easier for you to understand. So it's a reciprocal of it. So conductivity is defined as the rate of heat flow to unit area of unit thickness of the material when there is a unit temperature difference between the two sides. So this unit of measurement is given by watt per meter degree Celsius. So its value varies between 0.03 for an insulating material and for insulating materials up to 400 or this thing. This is for 0.03 is basically for insulating materials, whereas it goes up to 400 watt per meter degree Celsius per minute. So to quantify the ease with which a particular medium conducts, engineers employ the thermal conductivity, also known as the conductivity constant or the conduction coefficient. So this they have a specific coefficient which is given by conduction coefficient, which is also K value. So conductivity, how do you give the conductivity? So this contains how much K, what is defined as the quantity of heat, Q transmitted in the time T through a thickness L. Okay, in a direction normal to the surface of the area due to the temperature difference. So it's talking about all these things put together. We'll look at the formula for you to understand. The thermal conductivity is a material property that is primarily dependent upon the medium space, the temperature, the density, and the molecular quantity. So there are 4 factors involved in this. That is your K, the conducting constant. Your A should be your area. Delta T would be a temperature difference, and D is nothing but your thickness of your material. Yeah. This let's look at that's what they have spoke about. Letter Q represents the amount of heat that is transferred in a particular time T. K is your thermal conductivity constant. A would be your cross-sectional area. Delta T is the difference in temperature from one side to the other side. And D is the thickness of your material. These factors can be seen visually in the diagram. Yeah. So conductivity, looking at your conductance. Conductance is nothing but the heat flow rate to a unit area of body when the temperature difference between the two surfaces is at least 1 degree centigrade. So it's talking about how much of the heat flow happens when your difference is just 1 degree centigrade. So this unit of measurements is given by watt per meter square degree centigrade. So this thermal conductance is nothing but the process of heat transfer from one part of a body at a high temperature to other low temperature. Coming back, it's talking about the same transfer of heat that is happening from a higher temperature to a lower temperature. Your resistivity or the R value is given by how is it given by? So your thermal resistivity or R value is nothing but your inverse of your thermal conductivity. So insulating materials are rated by your R factor. So how the conductivity is defined by the K factor, these are defined by your R factor. The higher the R factor, the more effective the insulation. So resistivity is basically the reciprocal of this quantity, that is 1 by K, measured in units of a meter per meter degree centigrade per watt. So better insulators, we usually have high resistivity values. It's talking about how this overall happens. Good conductors have good conductions, whereas good insulators have higher resistivity and low conductance. Yeah. So resistance of a body is the product of its thickness and the resistivity of the material and its unit. So you're talking about overall what exactly does overall resistance this power is. So your resistance, what you're trying to give is that you're not only considering the material resistivity, but almost also considering the thickness, because that also factors, right? Because the layers and layers as it goes through, the resistivity increases. So its overall resistance is what you're trying to calculate. This measurement is actually given by meter square degree Celsius per watt by watt. So R, this resistance is nothing but the B considering to be a thickness, this thing into your resistivity value, that will be 1 by K. So it's given by B by K, where B is the thickness is usually given in meters. Okay, so this I think we have got cleared the resistivity because it's a simple factor. Now looking at your conductivity is a material property and its ability to conduct heat through the internal structure. The conductance, on the other hand, is an object property and depends on both its material and thickness. Conductance equals conductivity multiplied by thickness in units of watt per meter square and degree Celsius. As conductivity is the reciprocal of resistivity, the total resistance of a material can therefore be given by its total thickness divided by total conductivity. So now how do you try and understand what is actually conductivity overall you speak about, right? Now you're talking about the surface conductance. Why do you have to understand surface conductance is because usually it's talking about the exterior surface, like how on the water you have a light film, and we consider that all the materials would have such. So in addition to the overall resistance of our body to the heat flow, a resistance is usually offered by its surface also. So where a thin layer of film separates the body from the surrounding air. So the measure of this surface or the film resistance is what we are talking. First, we try and understand, and thereby we try and derive the surface conduction factor. So it's usually denoted by 1 by F. So it's already like we are trying to give it as reciprocal. So F being the surface or film conductance. So the surface conductance includes the convective and the radiant components of the heat sheet and surface. So coming deep into that, so it's talking about air-to-air resistance. So if the heat flow from one air on one side through the body to the air on the other side. So it's talking about another factor. We're talking about so first we were talking about the material, yeah, the material resistance. Then we overall talking about the overall resistance, and then we are talking about the exterior film resistance. Now it's talking about the air-to-air resistance. So now when the transfer from one side to the other side happens, what is the resistance given by the air? So this heat flow from air on one side to the body to the air on the other side is considered. So in this cases, the both surface resistance must be taken into account. Instead of just one phase we are trying to consider, we have to try and consider two phases. So how is this air-to-air resistance important? So the overall air-to-air resistance is usually the sum of the body's resistance and the surface resistance. So where can you see if it's addition factor? So it's basically the resistance of the body, internal surface resistance and external surface resistance. So that is what it is. Now looking at your transmittance or U value. So as we spoke about earlier, how the U value is a very important key factor. So the reciprocal of this air-to-air resistance is the air-to-air transmittance or the U value. So it's basically that reciprocal. So you can get your by deriving your resistance, you can try and understand your transmittance of the U value. So its unit of measurement is the same as for conductance. It is given by watt per meter square degree Celsius. So this is a quantity most often used in building heat loss and the heat gain problems, and its use is greatly simplifies the calculations. So how do you actually get this idea? So in real life situations in almost all building components, the heat transfer takes place through usually three modes. So what happens is the wall receives heat through convection from the ambient air. Then through conduction, the heat gets transmitted up the inner surfaces where again the convective heat transfer due to the inside air and heat goes into the building. So then this term that it actually represents the overall thermal conductance from the outside to the inside, covering all modes of heat transfer. So this U value can be defined as the rate of heat flow over unit area of a building component through unit overall temperature, the difference between both the sides of the components. Yeah, the U value is an important concept in building design. It represents the air-to-air transmittance of an element. This refers to how well an element conducts heat from one side to the other, which makes it the reciprocal of its thermal resistance. Thus, if we calculate the thermal resistance of an element, we can simply invert it to obtain the U value. So after this, again the same thing. Or we could try and get one element, one data, and reverse it to find the other. So imagine like I have the resistivity value, I can get the conductivity. Yeah. So this U value is the property of a material. Thus, its units of watts per meter square Kelvin. So this means that if a one material had a U value of 1 watt per meter square degree Celsius, for every degree of temperature difference between the inside and the outside surface, 1 watt of heat energy would flow through each meter square of its surface. So, like, how do you understand? Like, how does when this transfer is happening? How does this? What is the value that we could consider? How do you actually calculate this value? Now, looking at the soil and temperature, what exactly it is? So, in the design of the buildings, for surfaces exposed to solar radiation to calculate heat gain, it is useful to combine the heating effect of radiation incident on the building with the effect of warm air. This can be done using solid at temperature concept. The temperature the temperature value is found out, which would create the same thermal effect as the incident radiation in question. And this value is added to the air temperature. So where Ts is equal to solid air temperature in degrees Celsius, To the outside temperature, I would be your radiation intensity, A absorption of the surface, FO on the surface conduction. So how this value is overall given above. So you could see how this during winters and summer, how the because of the heat transfer, the conduction and radiation, your building ends up transferring the heat to the outside, whereas in the summer all the heat tries and comes into it. Yeah. So this periodic heat flow, the diurnal variations produce an approximately repetitive 24-hour cycle. It is the increasing and the decreasing temperature. There is always a cycle that's going about, right? So this the effect of this on a building is that in a hot period, the heat flows from the environment into the building, where some of it is stored at night, and during the cold period, the heat flow is reversed from the building or the environment. So as we were seeing how the heat flow is happening from the environment in the building. So it's talking about how like similar in the image that we saw, how the heat transfer during the day and the night is, I mean, like in summer and winter is happening. Similarly, during the day and in night time, the heat flow happens. So in the morning, what happens is that the outdoor temperature increases. The heat starts entering the outer surface of the wall. Each particle in the wall will absorb a certain amount of heat for every degree rising temperature depending upon the specific heat of the wall material. And the heat to the next particle will only be transmitted after the temperature of the first particle has increased. So as it keeps on increasing, one particle or the other, like the heat keeps on transferring, and then thus the corresponding increase of the overall internal temperature will be kind of delayed. So because one particle and the next particle has to be heated up. So the outdoor temperature will have reached its peak and start decreasing. So the outer temperature has increased and it has started like transferring. But after a point, what happens is that it starts decreasing. But the particles are still like transferring heat. So from this movement on, what happens is the heat that is stored in the wall will be partly dissipated to the outside and partly to the inside. So as it's because it starts cooling now, right? So as the outer air cools, an increasing portion of its stored heat flows outwards, and when the temperature falls below the indoor temperature, the direction of the heat flow is completely reversed. So you could see that the overall the two quantities that actually characterize this periodic change are usually your time lag and your decrement factor. So what exactly is your time lag? The time lag is nothing but your time delay due to the thermal mass. Thermal mass is known as a time lag. The thicker and more resistive the material, the longer it will take for the heat waves to pass through. The reduction in your cyclical temperature on the inside surface compared to your outside surface is known as and the decrement. Thus, a material with the decrement value of 0.5, which experiences a 20-degree diurnal variation in the external surface temperature, would experience only a 10-degree diurnal variation in the internal surface temperature. It's talking about how this transfer of heat happens. Yeah. So the rule of thumb for massive masonry. So it's talking about what exactly would be a time lag. So if you have a massive masonry wall of your with earth, concrete, and all put together. So if you have a very thick wall, so your time lag will be 10 hours for each 0.3 meter thickness. So how does this impact your design? So this effect is particularly important in the design of buildings in environments with high diurnal range. In some deserts, for example, the daytime temperature can reach well over 40 degrees Celsius, whereas in the night it goes below freezing point. So if a material with a time lag of 10 to 12 hours is carefully used, then the low nighttime temperature will reach the internal surface around the middle of the day. So thereby cooling the inside air down. So it's talking about how your time lag can actually be used to your advantage. So similarly, the high daytime temperature will reach the internal surface late in the evening, thereby heating your inside. So it's talking about how the delay and the lag that is happening can actually be used to your advantage. Whereas in a warm and tropical equatorial climates, the buildings tend to be very open and lightless, so thereby this lag is not needed. So it's usually But then again, going back to very cold and subpolar regions, buildings are very thick and highly insulated. So they have very little exposed thermal mass, even if it is used for structural reasons. So it's talking about how you could see, like, to attain this basic mean climatic comfort zone, what and all are, like, the natural climatic conditions, your microclimate modifications, your passive systems, your active systems, all has to, try and achieve that one comfort zone is what we are trying to say. So this precisely controlled indoor climate can only be achieved by active or mechanical systems. So however, this may not be the aim of a building designers. So usually you have to depend on the mechanical system, but that's not what we prefer. So this passive design can be well attenuate the extremities of the climate and sometimes cause desired comfort indoors with little seasonal or diurnal variations. The passive systems may not provide 100% climatic control, but they substantially reduce the risk of the active systems and hence make them more economical. So looking at what exactly is the insulation. So insulation can actually help increase the time lag and the decrement factor and this helps in the heat balance of a building. The position of insulation related to the thermal mass has a very significant effect. It's talking about where you place the insulation also plays a very important factor. So with the 100 concrete slab, the placing of your 40 glass wool insulation gives the following variations. If it is placed under the slab, the time lag is only 3 hours, whereas it is placed on top of the slab, it's 11.5. How does this actually like affect you? Is what it affects you. So what happens is that the insulation on the outside reduces the heat flow in the mass and will take much longer to fill up the storage. So it's already like it's on the outside, it's becoming like a barricade to actually let it in. So if the wall is already heated up and then you act as an insulator, the effect is very less. Whereas when you stand outside and become stop it from coming in, so its effect is like increased. The insulation inside will not affect the filling up process, and although it will reduce the heat emission to the inside, it will not change the periodicity. So in hot climates, the aim is not only to reduce the heat entering the space, but also to dissipate as much of the heat stored to the outside. So an insulation on the outside or top of a slab will reduce the time taken for the heat to pass through, but does the same to the dissipation of the heat to the outside. So there is a possibility that by the morning, when the heat gain starts again, all the heat from the previous night might not have even starts leaving off or letting go dissipated. That will lead to the discomfort, and this can be avoided by good ventilation of the inner surfaces. Yeah. So that's what we're trying to see. Like, so this overall chapter is like, topic is about how you have attained all of understood like how this transfer of heat is happening and how different simple concepts of doing insulation and time lag and all of this can actually understand and how you could control your heat flow from matter. So that's about it for this chapter. So we'll be ending the session with this. So thank you.